Okay, in this short video tutorial, what we're going to look at is 4 example calculations where we're using the Doppler effect or the Doppler equation. Just to recall, the Doppler effect is the change in pitch or frequency of a sound that's moving relative to an observer. For this course, we're only looking at the moving source and a stationary observer, not one where the source and the observer are moving, and it's only in one dimension. We're not looking at if the object is moving at an angle compared to the observer, because there's different effects that take place. There are examples and calculations you can do and videos associated with that I've made on the website that you can check. So just to be aware that if this is the source frequency here and it's moving towards you, as it produces waves at very particular periods or frequencies. So, at a very specific, remember the period and frequency are inversely related. So if it's a high frequency, it's a low period. If it's a low frequency, it's a high period, meaning it takes longer for those waves to appear. Well, what happens is if the object is moving, then the waves that are being emitted are pushed closer together because as they're emitted, the object has moved forward. So the next one that gets emitted is closer to the previous one. And what you'll notice here is that you get small wavelengths. Well, remember the wave equation, V equals F lambda. Well, if the wavelengths are smaller, the frequency is higher. So see here, wavelengths are smaller and they're happening more frequently. So this guy's going to hear a higher frequency than what's actually being emitted from the source. That's if it's moving towards. If it's moving away, this wavelength gets bigger, right? Because it emits a wave, but it's moving away before it emits the next wave. It's moving away before it emits the next wave. And so the wavelength's higher, which means the frequency is lower. Bigger wavelength, they hit you less frequently. You go ding, ding. This one goes ding, 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 ding. And you'll get a lower perceived frequency, or the F2 will be lower. Obviously, if the source is not moving, V is 0, or V of the object is 0, then everybody hears the same frequency. If you reach the speed of sound, meaning that this object is moving at the same speed as the waves it's producing, you get a barrier right in the front. All the waves are crunched up together. And in fact, at that point, there is no Doppler effect because you've reached the sound barrier. Behind you, you get these massively spread out waves. If you break the sound barrier, it means that you're going so fast that the waves you're producing are actually behind you. And that's a really cool effect as well. So if you're going Mach 1, or above Mach 1, then you'll see that effect take place. So Mach 1 is just the speed of sound, and you'll be right on top of it. If you go on Mach 2, you're just leaving the waves behind you. And you can do that in a boat too. If you ever go on a speedboat, you'll notice that if you're going slowly, you'll see the ripples in front are close. The ripples behind are further apart. And as you go faster and faster, there's a speed. If you break the speed of water waves, the boat will be way in front of where the waves are being produced behind. It's the exact same thing in air, but you can visualize it in the ground, in the water. And remember, because the water is a very specific medium, the waves move at the same speed for everything in that area. All right, this Doppler effect calculator here allows you to calculate the apparent all of your stuff here for the apparent perceived frequency. You can also do the speed of sound in air. There's all kinds of cool stuff that you can do here. And that, I believe, was included this is the student's work from a few years ago. So let's take a look at just one last thing before we start. So here we go here. If I start this is a stationary source at a frequency of 100 hertz, and the observed frequency or the perceived frequency FO by this person here is 100 hertz because it's not moving. Okay, if I pause it, reset. Okay, now what I can do is I'm going to go faster. I'm going to go like 0.1 times the speed of sound. So 0.1 times 332 around there is about 33 meters per second. So if you're moving at 33 meters per second, that moving object, the waves in front are slightly compressed. The waves behind are slightly spread out. So you notice here the frequency is higher because these are getting hit more frequently than 100 times a second. They're getting hit at 111 times per second. Now, once it hits, it should drop to 100. and then drop. Well, it'd be 100 when it's right beside you or passes through you and hits you. But then see it drop to 91. Now, what you're going to notice is it's 111, which is 11 above the 100. Now, I think it's a little bit off because when it goes to the other side, it says 91, which is 9 off. It should actually be 89 when it passes by. And you can check that with your math, right? That should probably not be 91. That should be 89. Now let's see if we're going faster. So we'll pause, and I'm going to go 0.6. Look at that, 250 hertz. So it's 150 above, and then 63 below. So again, you can check the math on that. I think it should be around 50, but we can check the math to make sure that's correct. Okay, but you can see that they're compressed in front, so the frequency is higher. And when it goes behind, the frequency is lower, and so you get a perceived frequency that's lower. Okay, let's give it a shot. All right, here are, oh, that's a little bit fuzzy. All right, Doppler shift examples. You can follow along in your sheet. The perceived frequency is the, we did this derivation before, is the emitting frequency times the speed of sound over the speed of sound plus or minus the speed of the object. And the speed of sound is 0.6t plus 332. And also, we know that the speed of the wave is frequency times the wavelength, the universal wave equation that works for all waves, even light. All right. If a car drives past you while honking its horn, the horn emits a frequency of 512 hertz. So that's our emitting frequency, 512 hertz. It's moving at 25 kilometers an hour. So that's our VO. Now, we don't want it in kilometers per hour. So we want it, so we divide it by 3.6, which is the fast way. So it's about 6.944 meters per second. And it says the air temperature is 23 degrees Celsius. And it wants us to calculate the perceived frequency as it approaches you and after it passes you. So we're going to look at both cases. Well, the air temperature is there for a specific reason, because it wants you to calculate the speed of sound, because we need that in our equation. So we just do 23 times 0.6 plus 332. So we just punch it in our calculator. We go 0.6 times 23 plus. So it's about 345.8 meters per second. Okay, so now let's find the perceived frequency. So we're going to do the towards. Now, if it's towards, we know that the frequency should be higher. And if the frequency is going to be higher, the perceived frequency is going to be higher, we know that we want to look at this part right here, the plus minus, and say, well, if it's coming towards us, we need a bigger F2. Well, you get a bigger F2 by having a smaller denominator. How do you get a smaller denominator? You pick the negative sign. So our perceived frequency is F1 Vs over Vs minus VO. Frequency 1 was 512. Vs is 345.8 divided by 345.8 less the speed of the car, which was just the slow 6.944. So you're not going to get much of a frequency change, but it is still not zero. Okay, so we've got our denominator, and then we times it by the 512. We get about 522 hertz. So it went up by about 10 hertz. So the frequency shift the Doppler shift which is our delta F, is the absolute value of F2 minus F1, is 10 hertz. The reason we use the absolute value is because whichever one's bigger or smaller, it doesn't matter. The Doppler shift is 10 hertz. 10 hertz frequency difference. Okay, if it's moving now away, then F2 is less than F1. And that means we want the denominator to be bigger because we want F2 to be smaller. So we're going to use the positive sign. We write out the equation like this. Vs plus, my pen is dying a bit, so sorry about that. And we go F2. So now it's 512. 345.8 all over 345.8 plus 6.944. And F2 is, and we just plug it in, so we get 3. I like to do the denominator first, so I do 345.8 add 6.944, and I get a value. I invert it, then I multiply by 512, and then I multiply by 345.8. And I get 502. This is what I was talking about. In the other equation, the calculation was off. It's 10 below because your Doppler shift, the actual Doppler shift here, F2 is smaller now than F1, and so you get negative, but because it's absolute value, you still get 10 hertz. 10 hertz. So the Doppler shift stays the same. So once you know the Doppler shift, it's whether it's moving towards you or away, you can just out of subtract that value off. Okay, let's take a look at the next example. I'm just going to get you started on the rearranging. I'm not actually going to do the question for you because you can figure that out on your own based on what we just did. Train's moving towards you at 180 kilometers an hour. So that's our VO. 180 divided by 3.6 is 50 meters per second. Okay. The temperature is minus 10 degrees Celsius, so the speed of sound is slower. And you perceive a frequency, so your F2 is 400 hertz. Calculate the frequency the horn is actually emitting, F1. Okay, now it says it's moving towards, so you should highlight that. So if it's towards, then what I always write down is that the F2 that you're perceiving is bigger than F1, which means that you need to use the denominator, a small denominator. So we're using the minus sign. So you always, if you don't do this, you're going to be in real trouble because you're going to rearrange this formula, get it, and then say, and another question will say it's moving away, and you can't just use the same formula. You got to rewrite it and rearrange the formula again. Okay, you're going to use the temperature to find the speed of sound. I don't really care. You can figure all that out, but I just want to show you the quick rearranging because this is the hard part for some people. It's just the basic. It's actually the math that causes most of the problem here. So we're using the minus sign. So important. Don't forget that. Don't just memorize an equation. Do not do it. There's no point. This equation with the plus minus you memorize, but then rearrange it every time. You're trying to find F1, and you're like, okay, where's F1? Well, F1 is right there, stuck up there. So we got to get it by itself, cross multiply. Do this on your own, and then follow the tutorial afterwards. There we go. So now if I want F1, I just divide both sides by Vs. And F1 equals F2 Vs minus VO over Vs. Okay, there you go. That's only if it's moving towards you. Okay, let's see if the units work. Speed and speed gives you speed. Speed divided by speed gets rid of the units of speed. So this is meters per second divided by meters per second gives you 1. And then you're left with frequency, which is hertz. Hertz and hertz, you got it. Also notice, if the object is not moving, if the VO is stationary, what's Vs divided by Vs? Well, whatever, this doesn't matter what the speed of sound is, it becomes 1. So your F1 is equal to F2, which is exactly what you would expect for a stationary object. Okay, let's try rearranging some of the other ones. basically, once you do these examples, you have all the rearrangements, or at least the skill set to do those rearrangements. All right. Fancy car passes by you emitting a horn. So it's emitting a frequency of 700 hertz. That's our F1. As it passes by, you notice the frequency drop to 680. Just as moving away. The temperature is 32 degrees Celsius. You can find the speed of sound, and basically it wants us to find out how fast that car was moving. This is a way to figure how fast objects are moving. Think about it. When you're trying to find out how fast someone throws a baseball, you use a Doppler radar. They can measure the frequency change in the light that's being bounced off the ball. They can actually precisely get the speed. Same thing if you get caught in radar with a car, right? It's exactly the same thing. They're just looking at the difference in the Doppler shift, and that Doppler shift tells you the speed of the object. Also for galaxies moving away or towards us, that's how they figured out the age of the universe, right? So VO, this one's a little trickier. It's moving away. And since it's moving away, F2 is less than F1, which means we must be using the plus sign of the equation. So we write F2 equals F1 Vs over Vs plus VO, like this. VO stuck down there. Now, some of you are going to start to panic. You might cry a little bit, but just follow the math. Let's get this out of the denominator. Cross multiply. And again, try this on your own. Pause the video and go from there. There we are. Now, I can't get it out of here. It's stuck in a bracket, so multiply the bracket out. Good. Now I can get rid of this term while it's being added on that one side. So we just simply subtract it off the other side. Now VO is just sitting there. So we can divide by the F2. And there you are. This is if you're moving away, only for away. All right. Now what you might notice is that you probably could have actually simplified this a bit more. You could have gone VO equals, you could have common factored out like that. You could have common factored the Vs. And now you'll see frequency minus frequency is just frequency. Frequency over frequency becomes, the units cancel out. And so the speed equals the speed. And so hertz divided by hertz is 1. Then you have meters per second left and meters per second. So you know the equation must be correct. Now you can just plug in your values. You take F1, subtract F2, which is 20, divided by 680, times it by the speed of sound, which you can get from the temperature, and you'll find the speed of the object in meters per second. Again, this is only if you're moving away. If it was moving towards, this would have become a minus sign, and then you'd have to divide by a negative, and you would also get your speed. Okay. Again, try these on your own. Pause, rewind, do whatever you need to do. Okay, a train is moving at 230 kilometers an hour. Fast conversion, just about 63.88. Okay, blowing its whistle with a frequency of 650 hertz. You perceive a frequency of 800 hertz. What's the air temperature? Okay, now you're like, oh, geez, how do I do that? Well, what's air temperature? It's just speed of sound. You've already done this before. So really what you're trying to find is, what's the speed of sound? And once you know the speed of sound, you can use this formula to find out the temperature. That's it. There's nothing, this is the hardest one, I think, for most people to grasp, but let's write it down. So it says here, if F2 is bigger than F1, so F2, the perceived frequency is greater than F1, that means that it's moving towards, because the pitch is higher, which means that you're using the negative because you want the denominator to be smaller. Okay, so again, super important that you do that analysis first. Now you just write out the equation using the plus sign, And using the plus sign. What am I talking about? Using the minus sign. Since the denominator is smaller. Now you're like, now there's a panic. Now people are starting to cry. Because right here you've got your VS and you've got your VS. And you're like, well, how do I do that? How do I solve it when there's two VS's in there? And again, the rule of thumb is just don't panic, right? There's no point in doing that. Just follow the math. Again, just bring the denominator up. F2 VS minus VO equals F1 VS. You can't have VS's on both sides, so we just got to multiply the brackets out. Again, pause now and you can figure it out from here. Okay, now whenever you're doing math like this, you always want to bring terms to the same side that are the same, right? You've learned this in your math classes. So I'm going to do this a little fancy. I'm just going to take this minus F2VO and bring it over. I'm going to take this positive F1VS and subtract it off the other side. So this one gets added to that side. This one gets subtracted to that side. And again, whatever you do to one side, just do to the other side. See, minus F2, I just added it to this side, and this one I subtracted off this side. Now you're like, okay, there's a VS and a VS. Well, use the four-letter word of factoring, right? The F word, and it's factoring. So we go here and we say VS, F2 minus F1, F2VO, and there we are. Almost done. VS and F2 minus F1. And so now we check the units. Frequency, which is hertz, over frequency, which is hertz. Hertz over hertz is divides out to 1. And you have speed in meters per second equals speed in meters per second. You got it. Now look here. This is if you were moving towards. If you're moving away, the solution is a little bit different. Now again, once you get your value for this, you're then going to rearrange the formula for temperature, which you've done already in previous questions, which you know is just that formula, right, to find temperature. And you've already done that in the previous examples. Okay, so those are the 4 different rearrangements. And again, they're only for specifics like away or towards. If it changes, you can't just use this equation. For instance, if this one was moving away, that would be a plus sign, that'd be a plus sign, that'd be a plus sign, that'd be a plus sign. So then that would be, that'd be a plus sign, that would be a plus sign, that would be a minus sign, that'd be, you know what I mean? And you'd end up with a minus on the bottom. But you can figure that out on your own. Okay, I hope this helped, and good luck with the rest of the questions in the package.